So I'm Moon. Well, my full name is Moon Young, but I'm Moon, like moon in the sky. And I work at Robinhood. And I work on streaming platform. So we deal with all things Kafka and Flink related. We manage all our brokers, all our clients, as well as our various Flink clusters throughout Robinhood. And this is Tony Chen. He also works on the same team as me. And we'll be talking a little bit about Kafkaproxy at Robinhood, what it is, why we built it out, and so on and so forth. So here's a little bit of the agenda of what we're going to be talking about today. I'll give a little bit of a brief background on how Kafka is being used at Robinhood, as well as some of our services there as well. And we'll talk a bit more about why we even decided to build this thing called Kafkaproxy. We'll go a bit deeper into the inner workings of the system in general, as well as a few challenges that we faced while we were building this out and rolling it out. And we'll expand a little bit more on the future as well. So basically, this is a bit of a background of Robinhood and Kafka usage at Robinhood. So all of our application services, they all run on Kubernetes. And these are mostly Python and Golang services because we started out as a Python shop and then we quickly embraced Golang into our tech stack. And Kafka is pretty much the de facto asynchronous service-to-service communication method that we have at Robinhood. We do have a lot of usages for data ingestion and event ingestion as well. But I would have to say that most of our more pertinent use cases for Kafka is with respect to this asynchronous service-to-service communication. Basically, all services utilize Kafka in one form or the other, and all of our material services depend very heavily on Kafka. And to give a little bit of examples of how we use Kafka, all of our pricing information, they all flow through Kafka in one point or another. And this is probably one of the more examples of high throughput, low latency use cases that we have. And this include equity quotes, crypto quotes, options quotes. And all of our customers' orders at a certain point in time, they also all flow through Kafka. So whenever a customer places a trade on the Robinhood app, basically it's persisted through Kafka, and then downstream systems process given the specific messages that are in Kafka. So given Kafka is pretty important, our colleague Sriram actually gave a talk on this yesterday, but we've eliminated Kafka as a single point of failure for the order path. So we basically have a sharded Kafka setup for the order path, and then we have each cluster with racks in 3 separate AZs, so that even if we have a AZ failure, we wouldn't be able to, the critical order path would still be able to function nominally. So, with a lot of focus on reliability and stability on the broker side, we've kind of turned our focus towards more on our client offerings because, client offerings are actually as important as probably what you do on the cluster side. And that's mostly what Kafkaproxy is about. So basically, it's a sidecar container, and it's responsible for one thing and one thing only, and it's for Kafka consumption. So it houses the Kafka consumers, and it relays the messages that it fetches from the brokers over to the application container over gRPC. And we'll talk a bit more about why that, and then if there are any performance hits there as well, because it's another RPC hop from one container to the other. And we've decided to write this entire sidecar in Java using the open source Apache Java Kafka clients. And we'll talk a bit more in detail about why we decided to do that as well. Yeah. So this is kind of what our client stack looked pre-Kafkaproxy world. So you'd have your application pod happily chugging along with the application container. Inside of it, the application process will instantiate a consumer from our thin wrapper around Confluent Kafka Go called kafkahood Go. And then underneath the hood, Confluent Kafka Go spins up a librdkafka consumer. And that's basically where all the interactions from the broker happens. It fetches the messages, relays it back, bubbles it back to the Go side over Cgo, and then basically the application can happily chug along processing those messages. And this is kind of the world after Kafkaproxy at Robinhood. So in the pod, you have the application container, and you have our separate sidecar Kafkaproxy. The application container still invokes kafkahood Go, but instead of invoking Confluent Kafka Go and therefore librdkafka Kafka, it basically starts interacting with the Kafkaproxy sidecar over gRPC, saying, "Hey, I want a consumer." And so in the sidecar, we have this Java process running. And it basically instantiates this Java consumer on demand from the application container. And that's the one that's responsible for fetching things from Kafka brokers. And it relays that over back to the application container over gRPC. And we'll go into more details on like the client server like interactions between both of these containers in a bit more detail a little bit later. So a lot of people might be wondering like why. It's like you're just like lifting one thing and putting in the other. And so we had a few good reasons why we wanted to do this, especially because engineering resources were pretty scarce, and we had to get buy-ins from others in the org as well for why we wanted to invest in this specific system. So one thing was that we quickly found ourselves maintaining two different client sets here. We have the Python clients, they're very well used, as well as the Go clients. And we do have Robinhood specific logic that's scattered throughout these two different libraries. For instance, we have a lot of logic around dead letter queue, which like utilizes a retry topic as well as a Postgres table for persistence. And that sort of logic is scattered throughout both of these. And we found it really easy for one of them to have specific bifurcation of logic that doesn't exist in the other. And also we had quite a bit of logic around multi-cluster producers as well as consumptions. Because we have that charted Kafka setup in the critical order path, our library wrapper has actually espoused a lot of the logic for dealing with, how do you consume from multiple different consumers at once and make sure it's seamless. And so it became really easy for us to, miss updates in the other, basically have different sets of logic in one versus the other and different confusing client behaviors. And it was a little bit difficult for us to actually maintain both of those. Also, another thing was because we had these two different sets of libraries that we were managing, observability also somewhat suffered because you would add specific metrics to one side, but then you would forget to edit to one of them. And so our clients found it really frustrating at times where we were like, oh, like why doesn't this metric exist here? It exists in the other one. And it would be like, oh, we forgot to do it. Also, this is probably something that's somewhat specific to Robinhood, but it's probably something that a lot of folks who utilize a monorepo kind of run into. And so at Robinhood, basically, if you make a change to a first-party like library, and the change lands on the main branch, you're basically at the mercy of application teams in terms of when that change gets rolled out to their services. And especially at Robinhood, where a lot of these services get deployed after market close for obvious reasons. This means that if you make a pretty big change in one of these first-party libraries, you actually have a fairly wide blast radius. So if there's a specific bug that you introduce, and because Kafka is used in all the material services, it means that you basically have a wide set of material services that could go down at once. But we actually thought about this with respect to sidecars previously because we had quite a few outages with respect to sidecars. And so we have this framework where for sidecars, you can basically roll things out in a more controlled manner so that sidecar changes will actually land on the least material services first, and it will go to the next set of the more important services. And at last, it would actually touch the most important services. And this life cycle of the changes reaching to prod for these material services can last from like 3 to 4 weeks from when you land the change to when it actually gets released. And so it's more of a very like gradual change, and it gives us a bit more psychological safety because we don't need to be super, super paranoid that we're going to wipe out our entire fleet with a bad change. Also, this is something that we had anecdotal experience in terms of trying to debug certain resource utilizations. So with the separation of concern of the application container as well as the library, which is now espoused in a sidecar, you have exact telemetry into the actual consumption that's happening. So before, whenever we would introduce some form of performance regression on one side, it would be a witch hunt trying to figure out, hey, was it the application team or was it us? Especially if this arises in only a few or even a single service. But because you have this specific separation of concern between the application container and the consumer sidecar process, you know exactly who's to blame at a specific point in time. And this kind of ends that witch hunt a little bit earlier for us and gives us a bit more of velocity in trying to debug what's actually happening underneath the hood. And this is something that we probably thought really, really hard about. Because now the sidecar process is in a separate container, we quickly realized that we weren't really bound by the specific languages that our application teams were using. We were very happy consumers of Confluent Kafka Go and Confluent Kafka Python because underneath the hood, librdkafka Kafka is a fairly well battle-tested library. But this kind of reminds me of that XKCD blurb about, the entire digital world. And then there's that one guy in Nebraska, supporting that one library. And that has been the case with librdkafka Kafka for a fairly long time, where that one guy in Nebraska was that one guy in Sweden. And he actually worked for Confluent. I'm not sure if he still works there anymore, but at the time, we had a few bad interactions with our usages of librdkafka Kafka back in 2020, where when a group controller churns, our consumer groups were stuck in a rebalance loop, as well as if you try to commit during a rebalance loop, you could actually have a consumer group that never recovers. And obviously, all these things actually got fixed fairly quickly. The fixes got rolled out, and then we were able to bump things up. But organizationally, with heavy, heavy dependence on Kafka, we took a second look at it, and we didn't want to have any sort of single point of failures at any point in our stack. So with team members that actually use and vouch for performance of Java, the Apache Kafka Java clients, as well as the fact that a lot of these KIPs happen to land on these Apache Java clients first, meant that basically we consider Java as perhaps the better language to go forward with respect to this sidecar container. And we kind of made a gut shot decision. And this is something that we are constantly revisiting because now the situation with the librdkafka Kafka is actually a lot better. Confluent has actually officially put it underneath its wings and has put more development support to it. And so we're happy to revisit this later down the line as well as we further roll this out. But at the current moment, we're utilizing Java for this sidecar. Cool. So with that being said, this wasn't super straightforward or easy. We had a few hurdles that we had to overcome to make this sidecar even viable in the first place. So one thing is that before in the pre-Kafkaproxy world, you have these consumer process in the same container as the application process. So if the application container gets killed or it dies for some reason, your consumer was going to die along with it. And you didn't really have to worry about this synchronization between the state on the consumer side versus what's happening on the application side, because they're all happening at the same time. But if you actually move them out into separate sidecar, the consumers into a separate sidecar, you can have the application container dying at any point in time, and you can have the sidecar process die at any point in time. So we had to find a way to figure out how to sync the states in between both of them. And my colleague Tony will kind of go into more details on how we did that in a little bit. Also, like I said before, librdkafka Kafka is a battle-tested library and it's very, very performant. Although we were using Confluent Kafka Go for our more performant services, it still utilizes Cgo, so maybe there's a little bit of performance hit there with respect to Cgo. But still, we weren't sure whether or not if we were to utilize the Java sidecar and the Java Apache Kafka client with the gRPC overhead, with the messages being relayed over back to the application container over gRPC, whether or not we could actually meet the needs of the most performance systems that we had. And so this was something that we wanted to really, really test, and as well as fail fast if this wasn't something that was feasible. Also, lastly, migrations are never fun. It's never cheap. But the way that we decided to approach the sidecar in the first place, as well as our implementation change underneath the hood for our library, meant that we didn't need to depend whatsoever on our application teams. And we could do this migration kind of silently underneath the hood without them actually noticing. And yeah, my colleague Tony will come up and kind of explain a little bit more on the inner workings of our sidecar, as well as how that design kind of helped us mitigate some of these hurdles.
Thank you, Mew. And hello, everyone. My name is Tony Chen. I work with my colleague Moon here at Robinhood and the streaming platform team to manage Robinhood's streaming infrastructure. So before I dive deeper into how we overcome the hurdles in this project, let's go through the gRPC contract between the sidecar and application containers so that you have the background information to understand the hurdles that we overcome. First of all, I want to emphasize that both the application and sidecar containers have their own gRPC server and client. This means that the application container can send gRPC requests to the sidecar container and vice versa. When the application container starts running, it sends the register consumer request to the sidecar container. Once the sidecar container receives this request, it creates a Kafka consumer and sends an OK response back to the application container. Once the application container receives this OK response, it sends the gRPC request start consuming immediately, and the sidecar container starts this pull and push loop, as shown by the loop box in the right diagram. During this pull and push loop, the Kafka consumer in the sidecar container pulls messages from the Kafka cluster and pushes them to the application container via the gRPC request handle message. Once this application container receives these messages, it processes them, and if it successfully processes these messages, it sends an OK response back to the sidecar container. At any point of time, if the application container needs to stop message processing, it can send the gRPC request deregister consumer to the sidecar container to notify the sidecar container to close the Kafka consumer and clean up any resources related to the Kafka consumer. Once that's done, the sidecar container just becomes idle. Okay. So this is one of the hurdles that Moon mentioned, and over here, as Moon mentioned, all of our application services run on Kubernetes, and in this new world with Kafkaproxy, we need to make sure that the Kubernetes pod can remain healthy throughout their life cycle. While our Kubernetes pod is running, it can become unhealthy due to many different kinds of scenarios. For example, when a container uses more memory than the limit set, the Kubernetes controller can come in and kill that container and then make the Kubernetes pod unhealthy. This slide illustrates two particular failure scenarios that we have to deal with. As shown in the top right part of this diagram, the application container can become healthy, or the application container can die, and the sidecar container is still running. In the bottom right part of this diagram, if the sidecar container becomes healthy and the application container is still running, the Kubernetes pod can become healthy in this state. To deal with situations like this, we designed a unidirectional health check mechanism in the Kafkaproxy to handle these failure modes. The unidirectional health check is designed so that when either the application or sidecar container dies, the healthy container can detect this and wait for the dead container to become alive again. This health check is implemented in the gRPC request handle message, which is that gRPC request that's sent from the sidecar container, to the application container with messages from Kafka. When a handle message request is sent from the sidecar to the application container, the application container records the timestamp of this request as a heartbeat. If the application container doesn't receive another heartbeat within a certain timeout, it considers the sidecar dead and tries to register new Kafka consumers again. Once the sidecar container is alive again, the gRPC requests from the application container can re-register consumers, send that start consuming request, and start that pull and push loop in that sidecar container again. On the other hand, when the sidecar sends messages to the application container, if the sidecar doesn't receive an OK response from the application container, it will retry sending messages to the application container for a certain number of times. If the sidecar container doesn't receive an OK response from the application container within a certain number of times, it will consider the application container dead, and to deal with that situation, the sidecar container would close its Kafka consumer, clean any resources related to that Kafka consumer, and then become idle again. Okay, over here we're going to show a demo where in the happy path, both application container and sidecar container are healthy and running all the time. So, okay. Over here in the top panel, I'm printing out logs from the sidecar Kafkaproxy container. And then in the bottom panel here, I'm going to start off the application container and it's printing out the logs from the application container. So once the application container comes up, it's going to send that registered consumer gRPC request to the sidecar container and immediately send that start consuming request. Once the sidecar container receives that start consuming request, it starts this pull and push loop. As you can see, it's pulling messages from Kafka and then sending them to the application container continuously. So this will keep on going on, and eventually I'm going to gracefully shut down the application container down here in the bottom panel. So once that happens, when I gracefully shut down the application container, it's going to send that deregister gRPC request to the sidecar container. Once the sidecar container receives that deregistered consumer request, it'll close that Kafka consumer, stop that pull and push loop, and then become idle. And then eventually down here, the application container just closes and exits. Over here in this next demo, I'm going to show one of the failure modes where the application container dies unexpectedly. All right. So over here, the top panel prints out the logs from the sidecar container, and the bottom panel prints out the logs from the application container. So the pull and push loop has already started in the top panel here. And over here, to simulate the application container dying, I'm going to kill the application container process with kill-9. So once that happens, the application container does not send any responses back to the sidecar container. And the sidecar container does realize that, and it'll retry sending messages to the application container. So it's going to retry a few times over here. And with the health check mechanism in the sidecar container, once it realizes that the application container is dead, it'll close the Kafka consumer inside itself, clean up any resources related to that Kafka consumer, and then become idle. All right. So that was one of the first hurdles we had to overcome. Over here in the second hurdle, it's on the performance between Java and C. Yeah. So when we were planning out which services we wanted to migrate to Kafkaproxy first, we picked services that had the highest throughput because we needed to make sure that Kafkaproxy could meet the SLs and SLAs of these services. We could have started
think you're on the wrong slide.
Sorry about that. Realized that I was on the wrong slide here.
Oh, yeah. Maybe just go with this. Yeah, there it is.
Thank you. Okay, sorry about that. Okay, so back to the second hurdle over here, talking about performance differences between Java and C. When we were planning out which services we wanted to migrate to Kafkaproxy first, we picked services that had the highest throughput because we needed to make sure that Kafkaproxy could meet the SLs and SLAs for these services. We could have started with services with the lowest throughput so that we had more time to iterate on Kafkaproxy. However, with this strategy, if we discovered in the end that the highest throughput services were not as performant with Kafkaproxy, then a lot of time and resources would have been wasted in this project. It was important for us to fail fast to realize if this project was feasible or not. One of our highest throughput services needs to process up to 30 million messages per second at market open. And this graph here compares the end-to-end latency of the service between the Liberty Kafka version and the Kafkaproxy version. Liberty Kafka is implemented in C, and the Kafkaproxy is implemented in Java and uses the open source Java client. Over here in this graph, the green line is the Liberty Kafka version, and the yellow and blue lines are the open source Java client that's used in the Kafkaproxy. On this particular market day, the Kafkaproxy version in the blue line actually performed better in terms of end-to-end latency than the green line. However, as shown in the yellow line in this graph, the yellow line is also a Kafkaproxy application, and it didn't perform as well as the Liberty Kafka version in the green line. This actually varies on different market days, and it's not like the Liberty Kafka version always performs better than the Kafkaproxy version or the other way around. At the end, we realized that sometimes we had to actually go into application code to make some optimizations there. And actually, by optimizing our application code, we can make either Kafkaproxy or Liberty Kafka version more performant. So, like, this point from this graph is to show that even though with the Kafkaproxy, we have the gRPC overhead, and now we're using a Java client instead of a C client, it actually does not introduce that much latency or overhead into our application service. And at the end, it actually avoids all the variance and performance dependent on the application code. And the last hurdle that we had to overcome here was our migration story. So at Robinhood, we have close to 100 services that consume messages from our Kafka clusters, and it would have taken forever if every service had their own pattern of consuming and processing messages from Kafka. Fortunately, before we started developing Kafkaproxy, most of our Golang services were importing our Kafkahood Go client library wrapper and using APIs similar to the ones shown on this slide. When application teams import Kafkahood Go, they would create a consumer, start consumption, and invoke a callback function for message processing. The callback function contained business logic that was specific to the application team service. So since most application teams were already using these APIs, we did not need to modify the application team's code that much, and we only had to modify the underlying implementation of these APIs so that they communicate through Kafkaproxy instead of communicating directly to the Kafka clusters. All right, so forward looking. So now that we have Kafkaproxy, how can we further streamline our operations and simplify our systems with Kafkaproxy? We have data letter queues implemented in our client wrappers to store poison pill messages, and they're implemented separately in both of our Golang and Python client wrappers. With Kafkaproxy, we can extract the data letter queue logic from these client wrappers and centralize them in Kafkaproxy. Next, Kafkaproxy allows us to have unified telemetry and tracing across our Kafka messages. We recently implemented tracing in our Kafka clients, but we had to enable them separately for our application teams. Kafkaproxy will allow us to easily enable tracing for all application teams. It will also allow us to easily add spans to our traces for Kafka messages in one location, which is the Kafkaproxy, instead of in multiple application servers and multiple client wrappers. Third, if an application needs to consume messages from multiple Kafka clusters, a client wrapper needs to instantiate multiple consumer managers in order to register multiple consumers for these different Kafka clusters. Eventually, we can further simplify this logic so that the client wrapper only needs to send these configurations in one gRPC request to Kafkaproxy, and Kafkaproxy will handle all of the consumer management for these different Kafka clusters. Last of all, we can decouple the Kafka producer logic from the application logic and incorporate these producers into the Kafkaproxy. This will allow us to have exact telemetry into resources devoted to producers and consumers and all of our Kafka clients in general. Okay, so some of the takeaways over here to conclude this presentation. First, as mentioned, one of the problems or hurdles that we had to overcome in terms of Java versus C performance, it was important for us to pick the highest throughput use case or most performing use case so that we could determine if this project would be successful or not. It's definitely important to fail fast instead of investing too much time and effort into this project and realize that it would not work for our highest throughput cases later on. Next, it was important for us to make our migrations as seamless as possible for our application teams so that we didn't have to modify our application teams code much and did not have to involve members from the application teams much. And mostly it was our team, streaming platform team, that handled the migrations, and we only had to modify the underlying implementation of the APIs that they used. Last of all, with Kafkaproxy, it will enable us to introduce new languages and help application teams create services that require new languages. If an application team ever needs to use another programming language, we could create a very, very thin client wrapper and for these new applications so that they only have to worry about the business logic in the application code, and all the Kafka consumer logic is all handled in the Kafkaproxy. Okay. That's all we have for today's presentation. Thank you all very much for coming. I'd like to take this opportunity to acknowledge all the team members that worked on this project, including Wenlong, Sriyam, Sean, Chandra, Vijay, and Mia.